Hello, welcome back to my YouTube channel. Today I'll be coding out those problems that I derived yesterday for the steady state equations. It's from this video right here. Uh, from this video, I messed up I didn't really mess up, I just forgot where the I had the sign values down here for like the differential change in height, with respect to time, but I didn't put the sign where h1 minus h2 was, where that was supposed to be, like right there. But anyway, that was supposed to be there, but just to clarify. So I'm going to be coding it. That's where that came from. So today I'm going to be coding in Google Collaboratory. One second. Let me open up my. Okay. Hold on. Right, there's that. Okay. All right. So here is the start of my coding. So right now we're going to have all the imports. Well, here's the problem statement. We go off that. Today I'll be coding two spherical tanks of what I just solved, derived for, that are open to the atmosphere. They have radii of R1 with 4 meters, R2 is equal to 2 meters, and are connected at their bottoms with pipe area of A1 to pipe area of A12, that's what we're going to call it, is 0.2 meters squared. Both tanks have an inlet flows and are at initial steady state heights between 5 and 3 meters. And then we're going to be solving for at t equals 100. If the flow is reduced to 80%, where's the height going to be at? And then we're going to increase the other flow for at 250%, when t is at 200 seconds. So I'll be going over that. But right now we just have all these imports. We have from scipys dot integrate import solve IVP. That is just that's used to help solve the differential equations, and they all need to be on the right side to do that. I'll show you what that means later on in the video. Import JAX NumPy as JMP. JAX NumPy is just a huge library of different functions that we use to code, like JAX or import JAX is like the same thing basically, but like we say like jmp.sign, jmp.py, and it'll have like the values already for us. Then we have from plotly.subplots, import make subplots. These are used to make subplots arrange in multiple different subplots. It's what we use to graph. It's what we use to, it just makes the graphs for us. Import plotly graph underscore objects as go. And that's just shorthand for the plotly graphs objects as go. We'll be using those also to construct our graphs. And then import plotty as plotty.io as pio is the same thing. It's just to help shorthand that when I'm coding later on. And then pio templates.default equal plotty underscore dark. You can make that dark or white. It really doesn't matter. It's just if it's a theme for my collaboratory, if it's in dark. Originally it was in white, but I changed it to dark. All right, so let's start this off. So from the problem statements, you probably don't remember what I just said because I really don't remember them. We're going to start off with this. Now, I'll be creating these will be the initial values given to us to help calculate the model. So what I'll be doing is we'll have Tn equal Tn equal 500 seconds. Oops. Seconds. And then we're going to have square root times 2g. We're going to be using this number a lot. It came from our derived equations. I can type j square root 2 times 9.81. 9.81 is gravity. Ooh. All right, and then AC1, that would be the cross-sectional area of AC1. It would be 15 times pi. JMP times pi. The JMP is once again the same. It's like the library that pulls all of our different values for us. AC2, it's a cross-sectional area of 2. Be 3 times JMP dot pi. And then we have A12. That would be the that's the pipe connecting to tank 1 and 2. And that the area that's going to be 0.2 meters squared. 2 here. Meters squared. And then we're going to have A2. That is the out pipe, well, the pipe coming from out of tank 2. And that's also going to be 0.2 meters squared. All right. And then we were also given the initial height of tank 1 and the initial height of tank 2. Initial height of tank 1 would be H1I for initial height 1, and that would be 5 meters. And then H2I is 3 meters. Okay. So now we're going to be, I'm going to put in also the differential change in height with respect to time for tank 2. And this came from the steady state equations and what I derived in the last video. All right, so let me show you. And also it's a sign thing. All right, A12. So this is this initial flow rate of the pipe connecting to 1 to 2. To tank 1 to 2, my bad. So it'd be A12 times JMP dot sign. And then the sign value here is just in case that H2 is bigger than the H1, it like makes sure it's an absolute value so it doesn't mess with the flow, because the flow, if it's a negative, it can go a different direction. If it's a positive, it can go the wrong way. It just helps us keep track of that. JMP square root. JMP absolute value. H1I minus H2I. All right, hopefully. So that works. All right, and then I'm going to be, this is the initial flow rate of, just the initial flow rate from pipe 1 to pipe 2. I mean, pipe A1 to A2, basically. I'll just show you. Q12I, Q1I is equal to Q12I and then we're going to have the initial flow rate from pipe 2, Q2I, we're going to call it Q2I. And that's, we've already found this equation once again, but it's it's A2 times square root times G times JMP square root JMP absolute value from H1I minus H2I. Q2I. Oops, I messed that up. So just be H2I, my bad. E2 square root times 2. Okay. And then the flow rate for the initial, a second initial one, Q2I, flow rate from minus I, flow minus the flow rate from 1. So this is the initial flow rate of the fluid into the second state from the steady state. Initial flow rate from the fluid into the second state from the steady state. Okay. QTI, Q2I. All right. So next, new cell. I'm gonna see this runs real quick. Oh, something messed up. JMP is not. Oh. It only ran this cell, didn't run both of them. Type error, what? Unsupported type Q2I. Unsupported operon types for I. Did I mess up something? Maybe it thinks it's an array because of that. Let's see. Is it good? Yep. All right. Now it's good. Yeah, those brackets just thought it was an array for some reason. Well, because the brackets make a list, and I don't know. It just messed it up. Okay, so where do I want to go now? From here, we can define a switch, which a switch is a function that takes a number from a negative to positive infinity and makes the range 0 to 1 for the output. And that would be really useful for us right now because we'll be coding all of this and we'll have like 300 and 500 and something different points. And we just want to see the overall, like just the bread and butter of it basically. And the sigma function helps us do that. And that just makes the range from 0 to 1. So how we're going to do that is we're going to define the switch. Define the switch. That would be T. These are just variable names, but T. Why can't I type? And then from here we can return JAX. NN means neural network, and that is something that's super, super important because it can help solve hundreds of thousands of equations in seconds. And it's one of the main reasons why we used Google Colaboratory. Common functions in neural network libraries. All right, and then JAX and N, and then this will be sigmoid. Let's make it sigmoid. All right, and then it'll be T switch, and then divided by a scale. Then we're going to multiply it by variable 2 minus variable 1 plus variable 1. Now this function, once again, it just takes the negative, takes a number from the negative to a positive infinity and makes 0 to 1 on the range. Hopefully that's right. I think it is. We'll find out. Let's see here. Return JAX. V1 invalid syntax. Is it really that? All right, looks good. All right, so now I need to create two functions that will specify the flow rate into the first and second tank as a function of time. The functions will also decrease or increase at specific times. So to show you what that means, we'll be using the switch we just created when we're defining the different flow rates, and then we'll just be plugging them in for the times that we want them at. I don't want this out there. Okay. Q1 initial Q1N with respect to time now, because we're looking at when it increases or decreases at a certain percentage for time. This is return. Now we're returning the switch, and then we're just gonna from up here we can take these variables and now we can use them, and we're just plug numbers in what we need to. Q1Ni. And then 0.8 times Q1Y, because it's at 100 seconds, it's going to be 80%. We want it 80% in 100 seconds. So do that. Oops. Q1Ni, and it'll be 100. I think that's right. All right. So that's 80%. Yeah, that looks right. Okay. Now I have to find the steady state. The equation for the second one. Find Q2 in respect to time. Hopefully this works when it goes off to graph. It's always a hit or miss whenever I code, especially when we're recording. Return switch T Q2 at 250%. Or times in at 250% when it's at 200 seconds. Okay, so Q2 and then 200, and then our scale. We don't want it 1 because that'll mess with the like slope of the graph. It'll look really weird to just go like this, like really up. We want like kind of more evenly spaced out. So we'll put like 30. Should be right, hopefully. Let's see what happens when I return it. Looks good. Okay. So now we need to create a function that will return only the right side for the differential equation. We will be looking at the differential height with respect to time, but our initial values have to be removed now, like our Q12, like our Q12i, Q2i, H1i. We need to remove those now because we'll no longer want the initial, like the initial part of the equation. We want to specify whenever we can have those now. So to define that, we're going to have to make a new define, DHGT. DHGT be with respect to t, time, and height. So from here we can start. Pretty sure I have to. H1 will equal H of 0. Whenever I have brackets, that means it's in a list, and a list will create an array. And that's why we have the sigmoid function once again, because the array will be so big, have all these points, where it would just be really confusing what we're looking at. And then Q12, A12, has this times J and P again, sign, because once again, those offset values could cause a screwy thing with our calculations, and we don't want that. U2G is JMP dot square root JMP dot absolute value from H1 minus H2. Okay. And then Q2 would be times square root times gravity. All right, hopefully this works. So Q12 is just, the flow rate for the pipe 1, 2, connecting to tank 1, 2. And then this is the outlet. Q2 would be the flow rate coming out. SQ 2G times JMP dot square root of H2. Okay, that would be height 2. All right. And then again. So when I return this JMP and make it, see, I'm just gonna hit return JMP as an array. And then, so from here, we can do bracket Q1 and T minus 2 divided by the cross-sectional area. I wish I could make this stuff go away. Okay. So just be Q1N, respect to time, flow rate of 1, initial flow rate coming in, and plus Q12 minus Q2 divided by the cross-sectional area of those three. Okay. Divide. Oops. I feel like there's gonna be a problem here somewhere. Definitely. All right, said it was good. Surprisingly. Oh, oops. We need the final time too for the tanks. So 200 plus 300 is 500 seconds for the second tank. So T and it would equal 500. And this is the final time for second tank increase. Okay. Add cell. All right, so now we're going to be using a new function, which I've never seen before until class. It's called the Radu method. And it's basically, it's like a differential equation calculator, kind of. Basically, no, it is. And it's used to solve initial value problems. So what you do is, that's also why we have import scipy.integrates import solve IVP. That's where this comes into play now. So we'll hit solve IVP, initial value problem. And then we connect it to the model we just made, the DHGT one. And then we have to type in a bunch of different things for it. All right, so time span, all right. It'd be from 0 to n, I'm pretty sure. Yeah, 0 to 500. Okay, and then this one will be from initial height. yeah, initial one height, so I think 5 it was, or 3 meters, to the second height, which was h2i. All right, and then our method is redo method equal, and then dense output, we have to put, it's just the output for the different equation, and we set true. Boolean structure, let's call it, I'm pretty sure. Dense output part. Oh, not plus, equal. Okay. Now we need our time plot. Oh, so we're gonna need that t plot, and that's going to be equal to jmp.line space. Line space is just basically what it is, a line space. We have to set our values now. It's basically like you're just plugging in parts of the initial value problem that we were given, and we can solve it on Python, which is actually pretty cool. So what this does is it makes the points have equally spaced points. I think we're having 250. Yeah, let's just say 250. That should be good. We'll put 251. Really, all right. Let's put 251. And then we make solution equal res.solution t plot. This accesses the solution from the array we created, so we can grab points from the array. And that's why we're going to have this now, solution bracket 0. I mean, list 0, and it just grabs every points from that target area. And this will be the height of the first tank. It'd be equal to the height of the first tank. Yeah, the first tank. This is weight. Okay, so solution equals 0. And then solution 1 equals that. Okay, I'm going to add cell. Oh. Okay. Here, wait, I'm just going to put, this will be the height of the first tank, height of the first tank. The height of the second tank, solution down to 1. All right. Height of the second tank. What? Can't assign function. Oh, wait, let me run it all. That died really quick. Syntax error. All right, where's syntax error at? Solve IVP. Oh. Can't assign to literal. What? DHET equals H1. Can't assign true value? Why? Can't assign a function to a set. Hmm. Sure. Let me check the brackets again. All right, something happened. Code height wrong, but that's not the issue. What is the issue? Nope. Solve IDV missing two required potential arguments, T-span and YO. Maybe they're not caught right. Here, wait. Invalid syntax. DHTT, H1, H12, method. Dent output equal true. That doesn't need to be there. Invalid syntax. Unsupported types, unsupported operands for what? And DHCD. Did I have a comma there? Oh, that makes sense. Okay. Supported operon. What? I fixed it. One time, run all. Oh, died again. What? Switch takes 4 positions, arguments, but 5 were given. So there's definitely a comma missing somewhere. 1, 2, 3, 4. That is right. My switch is messed up. 5 were given. So 1, 2, 3, 4. Wait, 1, 2. Does it count that? I don't know. I think there's definitely has to be a comma there. Maybe out there. Invalid syntax. Nope. That isn't. Hmm. Think I got it fixed. It was in the switch error. There's a switch. It just didn't work because I had a comma here. I don't know why. Right now it works, surprisingly. Okay. So like what I said, the solution 1, I mean solution 0 would be the height of tank 1. See, I can just show you what I mean. Insert code, print. solution 1 equal to A. All right, yeah. So that's why we do a sigmoid function, because of this. The array, there's just so many points, like looking at this doesn't really make sense, but when you have a sigmoid function, it kind of dumbs it down a little bit and it's easier to look at when you graph. All right, let's start making the graph now. All right, so when I construct a graph, we'll be using fig equal make subplots. And what this does, it makes subplots. And then we're going to have rows equal 1, and columns equal 1. And we have fig equal make subplots, rows equal 1. Rows equal 1. Oh my god, I hate this. I hate that thing. I don't know how to turn it off. And then columns equal 1. 2, sorry. And then we have fig dot add dot underscore trace. And what this does is it just helps it helps identify what's going on. So you're going to have the plot. It helps show the plot in the solution. Here, I'll show you what I mean. And then go dot scatter. This is another function used to help graph it. And at x equals the time plot. Oops, t plot. And we're going to have y equals solution. Oh my. See, I don't know why that just pops up sometimes, but it's really annoying. Y equals solution 1, which is the height of tank 1. I mean, solution 0, which is the height of tank 1. And then we're going to name it name equal height 1. And then here we can have it row equal 1, column equal 1, equal 1. And this equals the plot for the first tank. All right. And then same thing again, but now we're going to do, instead of solution 0, it's going to be solution 1, and that's going to be the height for tank 2. Add underscore trace. Go dot scatter. This is going to create 4 graphs for us, by the way. The first 2 are going to be heights, and the second 2 graphs are going to show the flow rates. T plot y equals solution, comma, name is equal to height 2. Row is going to be equal to 1. Column is going to be equal to 1. Oh, crap. I don't know why that thing follows me around. I'll look at it later. All right. Now I need to graph. Now we need to show the flow rate. So fig dot add dot trace underscore trace. Go scatter x equal time plot, t plot, y equals solution. I hate that so much. Y equals solution. I feel like I have like a tutorial mode on or something. It just shows me every time there's Like, oh, this function does this. I don't know. It's dumb. And then y equals flow rate 1. Oops. Why am I? It has to be messed up. Y equals the flow rate of 1. And then that'll be n with respect to the time plot, t plot. And this name is going to be, I'll just call it flow n, flow 1. Flow, oops. Yeah. Flow rate 1. Or, yeah, flow rate for the first tank. That makes more sense. Flow rate. Okay. Now after this, we're going to have row equal 1 and column equal 1. I mean, column equal 2. My bad. So equal 2. All right. Now we have to do the same thing for this one. I'm just going to copy this one though. But instead of Qn2, it's going to be, Q1 is going to be Q2. I should have done that for the second one too, but this is going to be this flow rate second tank. And the second column is for the flow rate of the tank. Now, hopefully this works. I'm really hesitant about even trying, but let's see what happens. Oh, we don't want that. Close. Nope. All right. Invalid syntax. Where? Line 6. Y equal Q into. We have an extra comma. That's not it. Where's that? Is that really supposed to be there? If it's not, why is that invalid? I feel like that's not gonna work though. Let's see here. I'm just gonna delete this real quick. No, okay. That doesn't help. That doesn't help either. All right. What did I do wrong here? What? Runtime run all. Damn it. No, what? Okay, something's. Oops. Wait, what? Do I even need? Yeah, okay, I'm an idiot. This doesn't need to go here. I don't think. It just needs to go here. Well, syntax. What? Equal 1. There's nothing there. What is the issue? Row equal 1, comma equal 2. Oh my, come on. Nope. What is wrong with this? All right, and then that'll go there. That's not gonna work out, but I'm gonna invalid syntax. All right, those are like, I thought I literally copied it from that one. All right, I'm just gonna delete it again. Put this one down here. And then flow rate second tank. This will be a 2. Let's see what happens. Nope. I got an invalid syntax right there. Can't delete it. Name flow rate second one, bro. Literally identical. Yeah, maybe it's row invalid. Like what? Yeah, it's giving me that, but maybe if I do it like this. Column equal 1, row equal 1. Maybe because I don't have these can be in this. I don't know. Nope. Darn it. I mean, column equal 2, but it's still going to say invalid syntax. Equal 1. If I put it like in its own little box, fix this up. Row equal 1. There's no way it's going to work, but column equal to, please work. Damn it. Valid syntax. What the hell is going on? Taste, trace. Aren't these figured? This is trace. Wait. Nope. Well, I want to see what the graph looks like. Let's run it and see what happens. Unexpected EOF while phrasing. What does that mean? I feel like I'm almost there. It's just not aligning right. What does that mean to figure out a trace? Go scatter, xt equal plot, y equal q1 into t plot. Name is equal to flow rate and first tank. Do I need like a parenthesis somewhere else? I think I do. You need it like right here. That help? Our fun's little error are great. Maybe these are wrong too. I don't know. It's making me mad though. What? Is that an error now? Wait. Oh, I think it worked. It just, I don't know what that is. Red's not usually the value error. Trace back. Oh my gosh. How many things? How many things can go wrong? Invalid property specified for object or type. Row by column. Row by column. Isn't column equal to 2? Oh. Right. this. All right, I'm just gonna try this again real quick on the second one. I'm sorry this is taking so long. It's just very annoying debugging. All right, flow rate second tank. Row E column, the big Q2N. Like an idiot. All right, and this is supposed to be column. I don't know. Let's see what happens. I love this. All right. What is it saying here? Value error. What happened? Prop. It's something in the switch, I feel like. Is it the switch? Like, it's the switch. We can. Maybe this. Maybe let's make this like 250. And then, where's the switch at? I don't know. 130, 1 in 25. Maybe that's better. We're never in your graph, are we? What is going on here? Fig add trace go x equal t plot y equals solution 0. Solution 0, that we've already figured out what solution 0 is. There's a value problem. Sorry about this. Come on. Y equals solution. O x equal t plot. Go scatter. Make your add trace go. All right, let's try something else. 2, 1, 30. That wouldn't do it. There. Run it again. Make sure it stays, hopefully. Okay, there we go. Whew, that took forever, but thank you for coming to my YouTube channel today. I'm sorry about the delay. The debugging was very annoying, but I'm happy I got it done. All right. Thank you all. Have a good day. Let me stop share.